So, welcome everybody. This is Ravindra Thube, faculty at BYJU'S Exam Prep, and I welcome you all to the session of Champion Series. We are dealing with one topic today, which name is casting process. So, quickly share with your friends and just convey the message that we are about to start and kickstart the session. So, let's see that. So, welcome aboard on this scintillating Sunday. So, today is the Sunday. I must say that you must be having your dinner, and now we are going to start now session. So please join the session and convey this message to everyone that we are going to conduct this particular session right now, so that we'll kickstart everybody. Are you listening that? So let the student join and we'll start this particular, right? So write down your comment. Yeah. Write down your comment, something like that, any suggestion, anything, right? So otherwise we'll be there to kickstart our session, right? Fine. Okay, is there anyone who is watching this session? Is there anyone who is watching this session? So write down hi, something like that, so that we'll get to know each other. The students who are there, we can write down something so that we'll see that how exactly chemistry is there. Okay, hi. Rest of the students. Good evening, Sandeep. Good evening. We are about to start now. Yes. Good evening, Sandeep. Yes. Okay, fine. So rest of the students also, what to expect from this series? It's very simple that we'll cover some fundamental, which is nothing but what basic fundamentals are there related to the casting process, and then what we'll do, we'll particularly solve certain numericals, theory questions as well as numericals. We'll not waste a time as far as any kind of theory is concerned, but only a background little bit we'll discuss. Is it okay, everybody? Yes. So let's begin with that. So the first question is coming, what is casting? So we know that the casting is nothing but the process where molten metal is poured into casting cavity. And that molten metal, once is poured into casting cavity is exactly similar to component that we are interested to manufacture, right? Fine. And once it is allowed to solidify, by breaking the mold, casting component can taken out. Casting component can take out by breaking the mold. This is my simple casting process. So what we are doing, we are pouring the molten metal into casting cavity. Once the molten metal is poured into casting cavity, then it is allowed to solidify. By breaking the mold, then we take out the casting component. This is the journey of this casting process. Now in the casting process, entire process is classified under a certain categories or certain stages. So what these stages are, first of all, we have to make a pattern. Pattern is very important. Once we make the pattern, from that pattern we have to make what? Cavity. And for making the cavity we require mold boxes, the sand is required, the molding sand. The molding sand is combination of silica sand particles, clay, water or sodium silicate, dry sand or green sand comes in the picture. And then by ramming we'll create a cavity. Then withdrawing of the pattern is done. So once the cavity is done, then we have to pour the molten metal. Once the molten metal is poured, we are allowed to solidify, and by breaking the mold, casting component can taken out. Is it true? Yes. So we can say that there are typically certain stages are coming, and the first stage is nothing but what? Pattern making. Second is nothing but mold and core making, a pouring and solidification, fettling and the inspection. Right, fine. Now first question is coming, what is meant by pattern? Sorry. First question is nothing but what is meant by pattern. Are you alive, everybody? So pattern is nothing but the replica of the casting to get produced. So whatever the component that we are interested to manufacture, whichever the shape that we want, same pattern you have to make. But the dimensions need not require to same. Shape should be same, but dimension need not require to same. And why is it so? Because we know that whenever we are pouring the molten metal, it is poured into liquid phase, and then it will keep on shrinking till the solidification, and therefore casting size will be reduced as compared to pattern size. So we have to provide certain dimension. Addition has to be done. And whatever additional dimensions we are providing on the pattern, that is nothing but called as simply. What it is called as? It is nothing but called as a allowances. And there are different types of allowances comes in the picture. What is that allowances? Shrinkage allowances, machining allowances, draft allowances, distortion and shaking allowances. Is it accepted? Yes. Now let's understand, before solving the numerical, let's understand that we are pouring the molten metal. And can I say that whenever I am pouring the molten metal, the pouring temperature is generally, how much is pouring temperature? The pouring temperature is generally more than melting point temperature by 200 degrees Celsius. By what? 200 degrees Celsius. So we can say that pouring temperature is exactly equal to melting point temperature plus 200 degrees Celsius. Plus what? 200 degrees Celsius. This is nothing but called as my pouring temperature. Pouring temperature is exactly equal to melting point temperature plus 200 degrees Celsius. Now, whenever we are pouring the molten metal, what is the state? We know that the phase of the material is the liquid phase. Liquid phase is there. We have started pouring the molten metal. The moment we start, can I say that it will come into the atmospheric air, it will start dissipating the heat. Once it starts dissipating the heat, can I say that it will start dissipating the sensible heat and the temperature will continuously reducing. Now we know that solidification, everybody aware that. So solidification takes place at one constant temperature, right? Fine. That is called as freezing temperature. So slowly over the period of time, x-axis, what is there on the x-axis? The time is there on the x-axis, right? Fine. And temperature is there on the y-axis. So the temperature reduces and it will fall down to a one temperature called as freezing temperature. But still the body is in what? Liquid stage. Still the body is in what? Liquid stage. So what is happening? Temperature is reducing from the pouring temperature liquid to freezing temperature liquid. And when it is removing, when it is dissipating the sensible heat, can I say it goes on shrinking? It goes on what? Shrinking. And that shrinkage is called as liquid shrinkage. Now at the constant temperature, can I say that body will dissipate a which means latent heat, and we know that latent heat is utilized for what? Latent heat is basically utilized for phase transformation. So over the period of time, at a constant temperature, the liquid material will get converted to what? Solid, but it requires some time. Some time would be required. Temperature will remain constant. So now the body will convert into solid, right? Fine. The body is not solid. The grain growth will happen, the atoms will come together, the atomic bond formation will take place, crystal will form, solid is formed. But the temperature, if you see that, it is still a freezing temperature, but it's very high. Again, can I say that whenever the body is converting from liquid to solid, that is called as solidification is happening, there is also shrinkage takes place. And that is nothing but called as solidification shrinkage. But it is also in the form of liquid. Also form of liquid. So I'll say that A, this is point A, this is B, this is C, and C is nothing but freezing temperature, or it is basically a temperature which is at the higher temperature. Now again from that solid state, high temperature, body will come down to room temperature. Again it will dissipate the heat, and that heat is nothing but again a sensible heat, and the body will come to room temperature, and the state will be what? Solid state. State will be what? Solid state. So whenever the body is converting from freezing temperature solid to room temperature solid, again that phase also there is a shrinkage takes place. And therefore can I say that from A to C to be precise, from A to C, whatever shrinkage takes place, that shrinkage is nothing but called as what? That shrinkage is nothing but called as a liquid shrinkage. That is called as what? Liquid shrinkage. And whatever shrinkage takes place from C to, let's say that D, from C to D, or we can say that sir C to D, that is nothing but called as a solid shrinkage. It is called as what? A solid shrinkage. Solid shrinkage takes place. So can I say that liquid shrinkages will be compensated by providing riser, whereas solid shrinkages is provided or compensated by providing what? Shrinkage allowance. I hope you are understanding this. Right, fine. Let's solve the first question now. So we are waiting for that and we'll start solving this particular question. So what is the question? In solidification of metal during casting, the compensation for solid contraction. Solid contraction. What is meant by solid contraction? Solid contraction means what? The body is there at a freezing temperature solid to room temperature solid. When that transformation is happening, there is a contraction takes place. So that contraction is compensated by provided by oversized pattern, or bomb may be achieved by properly placed. Is there a theory class? No. There is no theory class. There will be what? Everybody understand that there will be only numericals will be solved. Yeah. We will be starting this particular. Good evening, everybody. So let me ask you a simple question now. Whether A, B, C, or D, what is answer? What is answer? Provided by the oversized pattern, or achieved by properly placed risers, or obtained by promoting directional solidification, or made by providing chills. What is the answer for this particular case? Whether A, B, C, or D, what is answer? So A is answer, B is answer, D is answer. Is there anyone who can tell me that what is answer? So we can say that, sir, we are providing what? Oversized pattern. And so whenever we say the oversized pattern, that means the size of the pattern has to be greater. Size of the pattern has to be greater. So because of the shrinking, casting will be what? Of a less size. So we'll say that, sir, A would be a perfect answer for this. What is that? A would be a perfect answer. That is by providing shrinkage allowances. Is that okay? Yes. Next question. Which of the following metals shrinks most from the molten state to the solid state? So now you need to understand that there are certain very interesting material. Amir, very correct. Now listen carefully that there are certain materials available. So whenever there is a liquid shrinkage takes place, aluminium shrinks by the maximum percentage in a liquid state. What is that? The aluminium material is the one which will shrink maximum in a liquid state. Please remember these materials. Otherwise that there would be a problem. Right? Liquid stage mein, who is shrinking maximum? Aluminium material. Then there is one material is called as brass material. Brass material shrinks by the maximum percentage. Brass material shrinks by the maximum percentage in a solid state. It what? A solid state. The brass is the material who shrinks maximum by the solid state. And if we consider liquid plus solid, that is a total shrinkage. Liquid plus solid, that is a total shrinkage. Can I say that, sir? Total shrinkage is a maximum. Total shrinkage is maximum in the case of steel material. In the case of what? A steel material, the total shrinkage is maximum. Point to be understood. Aluminum shrinks maximum in a liquid state. Brass is shrinking maximum by in a solid state. Whereas a total shrinkage is a maximum in what? Steel material. Now what is saying? Which of the following metals shrinks the most from the molten state to solid state? So can I say that total shrinkage is maximum in the case of what? Cast steel. So my answer will be what? Steel. Very correct. Very correct. Hani Amir, very correct. So I'll say that, sir. So B is exactly a correct answer for me. That is what? Cast steel will what? Particularly shrink in a maximum percentage. Right, fine. Total shrinkage will be maximum. Next, very correctly how to answer now. What is that? Which one of the following materials will require the largest size of the riser for the same casting? Same volume of casting. But which one of the below required the largest size of the riser? We know that riser, for what reason riser is utilized? Riser is basically utilized for what? For what? Compensating the liquid shrinkage takes place. So whichever material has maximum liquid shrinkage, that material will require definitely a largest size of riser, because riser ka purpose is that's to supply the extra volume of material. So aluminium, cast steel, steel and the copper. So what will be your answer? So whether A, B, C or D, which one required maximum size of riser? You tell me that. A, B, C or D. So it's very simple. Just now you told me that. Aluminium shrinks by the maximum percentage in the case of liquid. So liquid shrinkage is maximum in the aluminium. So therefore riser has to be provided there. Large sizes riser will be required. So I'll say that's A. Very correct. What is that? Aluminium. Aluminium will be required a largest size of riser. Please understand that is not the theory class. Right, fine. We are just giving the conceptual things. Right, fine. So next thing. Which one of the following materials can be used for making up the patterns? You tell me that. Which materials are used for? Whether aluminium, wax, mercury or lead, or all of them are used, or any one is not used. So we know that, sir, generally aluminium is a metal material or metal pattern that is also used. Then wax is also utilized as a material and metal as a pattern. Why? Because to manufacture extremely a great quality of surface. Because that wax is very, very soft in the nature. And whenever we are interested to manufacture small size of component, wax is utilized as a what? Pattern material. Mercury is also utilized. Now you'll say that, sir, in a room temperature, mercury is a liquid, but we cool them to minus 79 degrees Celsius. That is what called as cryogenic temperature. And at that particular temperature, we manufacture pattern. But sir, lead is a very softer material and the melting point temperature of lead is very less. So therefore, lead cannot be accepted. Lead cannot be accepted as a pattern material. And therefore, can I say that aluminium, wax and the mercury definitely can be used. But lead cannot be used. So what will be answer? Delhi D. 1, 2, 3. Very correct. Only one is giving answer. Rest of the students also has to participate. Rest of the student also has to participate. It's a very interesting session. Because you cannot learn to swim only sitting at the river of the bank. Right, fine. So I'll say that Delhi D. 1, 2, 3 is answer. Next question. During casting of a grey cast iron block of size of 100 by 20 by 10, shrinkage allowance is taken as 1%. What is the shrinkage allowance? Shrinkage allowance is taken as 1%. The ratio of volume of casting to that of the pattern. So what is the volume of that casting divided by volume of pattern? And there is given very clear. Grey cast iron is the material. Grey cast iron is very darling of GATE examination. Most of the times misconception is there. So when we talk about grey cast iron, you need to understand that liquid shrink. Grey cast iron don't behave in the same manner as that of the lot of engineering material. So generally what happens, whether it's liquid shrinkage or solid shrinkage, can I say material gets shrink and therefore size of the pattern has to be greater or riser has to be provided. But there is one twist here as far as grey cast iron is concerned. What is the twist? In the case of grey cast iron, wherever the liquid shrinkage takes place. So when the material shrinks from pouring temperature liquid to freezing temperature solid, it behaves in an opposite direction. So क्या होता है? It actually gets expand. It's actually get what? Expand. But now underline the statement. But once it solidifies, that is at a freezing temperature. Once it solidifies, after that temperature, when it cools down to room temperature, that contraction or whatever the shrinkage takes place in the solid state, that will be in line with the engineering material. In line with the engineering material. Which means that in a solid state, grey cast iron also shrink. Grey cast iron also shrink. Therefore, size of the pattern should be greater than the size of that particular casting. Do you understand that? No riser in the grey cast iron. There is no riser. Very correct. There is no riser in the casting. There is no riser in the casting as far as grey cast iron is concerned. Is it understood? Yes. So can I say that here it's very simple. Volume of this particular volume of casting. So how much will be a volume of casting? You tell me that. So I'll say that, sir, volume of casting is exactly equal to, this is length, width, thickness, right? Fine. 100 by 20 by 10. 100 by 20 by 10. This is volume of the casting. This is what volume of casting. Now we need to understand now what is volume of pattern. But the pattern side will be greater. That means each side should be greater by 1%, because we know that solid shrinkages is given percentage of what? Dimension. So therefore I'll say that if length is L1, so can I say we have to consider 1% more. 1% more multiply by 1 by 0.1. 1.01, that is 1% more dimension length. Width, if I consider W1, that is 20 multiply by 1.01. And if I talk about thickness, can I say T1 will be considered 10 multiply by 1.01. 10 multiply by 1.01. So this is nothing but a dimensions of respective of that particular pattern. So volume, how to calculate volume? Is there anyone who can calculate volume? Amla, your answer is wrong actually. Answer is wrong. It cannot be like that. So I'll say that, sir, volume of casting divided by volume of pattern, divided by volume of a pattern. So what is the volume of casting? So it's very simple that volume of casting is exactly equal to 100 by 20 by 10. So I'll say that it will be 100 multiply by 20 multiply by 10. Is it understood? And that is what exactly students are making mistake there. Please need to understand that. And what is this volume of pattern now? 100 multiply by 1.01. In the same manner, 20 multiply by 1.01. In the same manner, 10 multiply by 1.01. Is it understood? This is the way that it has to be solved. Now, what is the answer is coming? Answer will come 0.97. 0.97 would be my answer, and no other answer would be there. 0.97. 0.97 would be answer. 0.97 would be answer. So if I go that, and I'll say that C is exactly answer for me. 0.97. 0.97, that is exactly equal to C would be my answer. Is it understood? And most of the time students are calculating 1.03, and that's why we have selected this question. Grey cast iron has the negative shrinkage only in a liquid stage. Underline that statement. But when you talk about solid, it has a same. Do you understand how, Hania? Is it understood? We'll go to the next question. Right, fine. So the next question is that for making a cylindrical component of 50 mm diameter and 70 mm length by casting process, right, fine. The amount of draft allowance to be provided if the pattern is made by wax. Now it was given that, assume the casting is made vertically. Okay, whatever that casting, that cylindrical one of diameter 50 and the height is 70 mm, it has to be vertically cast. Understood? Now how much is the draft allowance is provided? Now we know that, sir, whenever we talk about draft, why the draft allowance is provided? The draft allowance is basically provided to make it easy for withdrawing the pattern from the mold boxes. And that's why the vertical edges, can I say these vertical edges are made into what? Inclined one by providing certain degrees, by providing certain degree angle. Is it true? Yes. So making the vertical walls of the pattern to inclined one so that withdrawing of the pattern from the mold box become easier. That's why draft allowance is provided. But now which material? Now most of this time students are discussing that, sir, that whatever the cylindrical body is a cylindrical one. So the outer surface is external. So on the external surface 5 to 8 degree allowance is given. C is the answer. But understand that what material? What material it is? Wax material. Wax material. Sir, is it general aptitude class? Manisha, is it look like a general aptitude? This is not a general aptitude, right? It is a casting, man. Right, fine. So what will be answer? Sir, wax material is used as a pattern material, but the melting point temperature of the wax is 70 to 100 degrees Celsius. So once we use the wax as a pattern material, we heat that entire mold up to 100 degrees Celsius. Once we heat that, entire wax solid will get converted into liquid. You invert the mold, and then we can take out this particular liquid easily. We don't require to provide any draft allowance. Even if you're providing the draft allowance, what will happen? Because this whatever the extra material is there, can I say it has to be removed by what? Machining process. It has to be removed by what? Machining process. So therefore I'll say that, sir, what would be answer? What will be answer? Sir, 0 degree draft allowance is provided. It is nothing but called as a 0 draft allowance. It is nothing but called as what? A 0 draft allowance is provided. 0 draft allowance is provided when we use a pattern as a a wax material or sometimes plastic material, polystyrene, PVC, polyvinyl chloride, in such a case, 0 degree draft allowance is provided. And therefore, I'll say that, sir, there is no calculation required. It's just a common sense. And let's see that how fundamentally correct questions we are talking about in line with our discussion. Is it okay, everybody? Is there any doubt? If you don't particularly answer something like that, what is sitting and watching? Are you there to monitor me to see that how the faculty is teaching? If not, then tell me answer. If you are a student, and if you are joining this session, I told you in the video itself, when you are coming, you should what? Give the answers. You should listen that. What exactly things are going on? I hope so you are understanding this, right? Fine. Next question. A casting size of 250 by 200 by 100 is to be produced by Invar material. What is the material? Invar material. By considering the shrinkage allowance alone, the ratio of volume of pattern to volume of casting is. Ratio of volume of pattern to volume of casting is. Volume of pattern to volume of casting. Sir, volume of pattern is given 250 by 200 by 100. I know that. Now, what is the volume of pattern? Sir, point to be understand that it is Invar material. It is which material? It is a Invar material. Do you understand what is this material? This material is what? Invar material. So can I say that whenever we talk about a Invar material, the coefficient of thermal expansion value for Invar material is 0. What is it? I'm talking about coefficient of thermal expansion value, alpha value is 0. What is it? Coefficient of thermal expansion value. If the coefficient of thermal expansion value is 0, that means even we heat it or even we cool them. So whenever we are pouring or it is coming down to room temperature, it is solidifying, can I simply say that there is no expansion? That means change in volume delta V is exactly equal to 0. Is it change in volume V is exactly equal to 0? Yes, sir. If the change in volume is 0, can I say that there would be no addition of the dimensions required to be provided in the pattern? Because why we provide the shrinkage allowance? Because the material gets shrink. When the material is getting shrink to compensate that shrinking, the pattern size is to get increase. But right now, the Invar material who has a thermal coefficient of expansion value 0, the change in volume is 0 in any case, whether it is a liquid or whether it is a solid. During a contraction, there is no contraction, alpha value is 0. So can I say that, sir, that ratio of the pattern and the volume of the pattern and volume of the casting will be what? Same. That is same means it is what? Equal to 1. It is not greater than 1. It is not less than 1. It is none. It is what exactly? C. C is exactly answer for this. Is it understood, everybody? C is exactly answer for this. C is exactly answer for this. Are you accepting, students, what exactly I'm talking about? Yes. I got scared that students saying that, sir, it is a theory class. It's not a theory class, first of all. Second, the students are saying it's an aptitude class or something like that. I don't know what is happening in the world right now. Are you watching, everybody? Yes. Next question. Right, fine. Chaplets. Now, can I say that chaplets are utilized to provide what? The support to that particular core. We know that hollow casting, if I ask you that, whenever we are producing the hollow castings, can I say that hollow castings are produced with the help of core? And the core can be get bend and break because of the buoyancy force, because of difference in the densities of the material of that particular core as well as liquid molten metal. So the chaplets are utilized to support it, right? Fine. And the chills are utilized for directional solidifications. We know that because if we are not directing the solidification of the material, what happens? The shrinkage cavity defects comes in the picture. Shrinkage cavity defects, and that's why chills are utilized for directional solidification. But chaplets are utilized for what? Support to the core. Core is supported by the chaplets. Core is supported by what? Chaplets. Right, fine. Now, let me ask you a question. Question number 1. Directional solidification in the casting can be improved by using. There are 3 words are coming here. The chills, and then the chaplets, and the paddings. So we know that, sir, chills are utilized anyway, directional solidification. Simultaneously, the paddings are also utilized for directional solidification, but the chaplets are not utilized. Chaplets are not utilized. Why? Because the main purpose of the chaplet, can you see that? This is nothing but my chaplet. The chaplets are utilized to avoid the bending of the core. It is supporting the core. It is just to use to support the core. Main function of the chaplet is to support the core. Right, fine. So I'll say that, sir, if the question is directional solidification in the casting can be improved. How it can be improved? By chills as well as by padding. But chaplets are not utilized. Most of the time students are using the chaplet also. They're saying, okay, chaplet. No, it's not. Chaplet ka main purpose kya hai? Chaplet ka main purpose is only to support my core. So chills and the padding. Can I say that Bombay B would be correct answer? Chills and the padding. Is it okay, everybody? Somebody write the answer. Eh? You don't know, these are questions coming from the heaven or what? Or hell or what? Or some different world we are talking about. Right, next question. The main purpose of the chaplet is, you tell me that now, just now I told you that. So the main purpose of the chaplet is to support the core. It's not a directional certification. I hope so. I understand this statement. So what is this? What is the answer for this now? Chintan and Sandeep Reddy and Manisha and then the Hania. Everybody, please write down the answer now. What is the answer? Yes, sir. Sandeep Reddy. Very correct. Love you, boy. So I'll say that, sir, to support the core. The main purpose of the chaplet is to support the core. Main purpose of the chaplet is to what? Support the core. So I'll say that Delhi D will be perfect answer for me. No problem at all. No problem at all. Is it true? Yes. Now, rigid metal pieces support the core are. Which are the rigid metal pieces which are supporting the core? Which are the rigid metal pieces which are supporting the core? I'll say that, sir, chaplets. What will be answer? Padding is utilized to support that particular, whatever the casting, I would say that, the cavity. Because what happens, corner portions cannot be manufactured very easily. Means what? The answer is that, what is meant by padding? So suppose this is the corner portion. Can I say this is the corner portion? So what happens during the ramming, the proper force cannot be applied to the corner portion. And therefore, can I say there might be loose sand particles might be available. And during the withdrawing of the pattern, that loose sand particles can be taken out, or that particle can be inserted into liquid molten metal, sand erosion kind of defects might be generated. And therefore, what we do, we provide a padding, like a cushion. And that is nothing but some extra material is provided like that. Right, fine. So this is nothing but like a padding. This is a way the padding is provided. So this is just a cushioning a sharp corners. So this is nothing but a padding. So this kind of is called as padding. Right, fine. But it is also utilized to what? It is also utilized for directional certification. It is also used for what? Directional certification. So I'll say that, sir, the chaplets are the one, right, fine. The chaplets are the one which are metal pieces which are utilized for what? Supporting that particular core. Is it understood? A is answer for this. Now, gating system, we know that the system through which molten metal entered into casting cavity, and here the beautiful questions are coming. And it has basically number of important parts. What are the important part? Number of important part. This is my pouring basin. This is exactly equal to my sprue, vertical sprue. This is exactly equal to runner. This is exactly ingate. This is my cavity, and this is exactly equal to my riser. Are you understanding? A number of beautiful questions are coming on this topic. What is that? This is my pouring basin. This is what exactly? Pouring basin. This is vertical sprue. This is what? Vertical sprue. This is exactly equal to runner. Right? Fine. Now, without wasting a time, let's ask you a simple question. Which one of the following is a correction or correct statement? Gate is provided in the mold is. Why the gate is provided? Now, you tell me that this is what exactly in gate. Right? Fine. Can I say gate is the area from where molten metal enters into casting cavity? Gate is the area where it is what? Entered into casting cavity. What is that? Chaplet gives support to core along with directional certification, sir. Oh, okay, fine. I'm sorry. It is not rigid cores are called. Yeah, chaplets are there. Right, fine. It's correct. So now what we are talking about, which one of the following statement? Gate is provided. So for what is gate is provided, there are three cross-sectional area. And you know that. What is the three cross-section area? One cross-section area is nothing but bottom of the sprue is represented by AS. Then horizontal runner cross-section area, it is called as AR. And the ingate cross-section area, it is called as AG. And there is one ratio is coming. What is that ratio? Ratio is called as gating ratio. So how that gating ratio is represented? It is a cross-section area of the bottom of the sprue. Then cross-section area of the runner is to cross-section area of the ingate. Cross-section area of the ingate. This is nothing but called as what? Gating ratio. Gating ratio. So can I say that, sir? The gate is provided for maintaining the discharge. What is that? Maintaining the discharge value, constant rate of discharge to the casting cavity, because through which molten metal enters into casting cavity. So can I say that my A is a perfect answer for this? Can I say that A is a perfect answer for this? Is it okay, everybody? Chintan, is it okay? Yes. Now you solve the next question. The gating ratio 2:8:1. The gating ratio is what? 2:8:1. For copper in the gating system, design refers to ratio of areas. So it's very simple. Just now you told me that it is area of the sprue to area of the runner to area of the ingate. So S stands for sprue, R stands for runner, G stands for what? Ingate. So AS is to AR is to AG. So can I say the sprue, runner, ingate? What will be answer? What will be answer? A is the answer for me. So I'll say that, sir, A would be answer for me. Is it true? Yes. So A would be answer for me. Bottom gating system is sometimes preferred in a casting because of. Do you know the bottom gating system? So there are different type of gating system. Top gating system. Metal is entered from the top corner. Can I say that this is casting cavity? So metal is entered from the top casting. But when the height of the casting cavity is greater than or equal to 200 millimeter, can I say that this molten metal can be acting as an impinging force at the bottom, and at that portion, can I say that there will be a loose sand particles may get generated. Splashing can be happen, the turbulence can be happen, and therefore when the height of the molten metal or cavity is greater than 200, we cannot use that. Now we are utilizing bottom gating system. So where the material entered into what? From where? It is entering from the bottom. It is entering from bottom. So height of the casting can be anything. I don't have any problem. I don't have any problem in this particular regard. Is it true? Pressurized and non-pressurized gating system is also there. Yes, Chintan. Right, fine. And there is one parting gating system. It is entered from where? Center. It is entered from where? Center. Is it true? Yes. So can I say that generally the bottom gating system is utilized to reduce what? Splashing and turbulence. Splashing and turbulence can be eliminated. Splashing and what? Turbulence can be eliminated from this particular case. From this particular case. Is it understood? Yes. Next solve. Now you solve this numerical. Now you should be ready with the calculator, and you should be ready with the pen and paper, and then you tell me that. The height of the downsprue is 175 mm. Height of the downsprue is what? 175 mm. And it's a cross-sectional area at the base is 200 mm square. Cross-sectional area at the base is what? 200 mm square. The cross-sectional area of the horizontal runner is also 200 mm square. Okay, fine. Assuming no losses, the time required to fill the mold cavity of a volume of 10 to the power of 6 millimeter cube. Can you able to calculate? How to calculate the time required for filling up the casting cavity? Sir, it's very simple. How to calculate? Sir, it's very simple. Can I say that, sir? Time required for filling up the casting cavity. Time required for filling up the casting cavity. How to calculate that time required for filling up casting cavity? It is exactly equal to volume of cavity. Can I say that? Volume of cavity divided by flow rate, or it can be called as discharge. And the flow rate is nothing but choke area multiplied by velocity of molten metal into gating system. And the velocity of molten metal in the gating system, 2 into G into what? HT. 2 into G into what? HT. Is it understood? 2 into G into HT. Right? Volume of casting divided by cross-sectional area into root of 2 into G into HT. Is it understood? Yes. Now volume of casting. What is the volume of casting? Is it given in the volume of casting? Yes, sir. Volume of casting is given. What is that? Sir, it is given that a 10 to the power of 6 mm cube is the volume of casting. So put it there. 10 to the power of 6. 10 to the power of 6. This is what exactly a volume of casting. Right, fine. Divided by cross-sectional area. That is choke area, which is minimum area. And that is considered as the bottom of the sprue only. And only one area is given. So bottom of the sprue cross-section area is 200 mm square. So you can write down that. Right? Is it true? What is your Telegram channel name, sir? My Telegram channel name is Ravindra Thube. Ravindra Thube. You can join this Telegram channel, and more beautiful sessions are coming. More beautiful sessions are coming. Ravindra Thube. Ravindra Thube. You can just go and check it that. So if possible, I'll just comment in a comment box also. Not required. Up till that, you just go and solve this particular question. So you just go and just solve this question also. Right, fine. So now can I say that it is given 200 mm square, 200 multiply by 2 into G, 9.8, or we can directly select 10 also. 10, right, fine. 10 to the power of 3, right? Meter per second square. But yet it has to be converted to what? Mm per second square. Mm per second. Sandy is correct. Delhi D is answer coming. Into height of the sprue. What is the height of the down sprue? Sir, height of the down sprue is 175. So I'll say that 175 answer is there. Very true. It has to be in a square root. It has to be in what? A square root. It has to be there in a square root. It has to be there in what? A square root. Right, fine. So time required, you can calculate that as simple as that. Nothing there. So I'll say that what is answer is coming? Sandeep Reddy, it is D coming. I don't know answer. You tell me that somebody. So is it that LED is coming? It's very simple. Volume by surface, volume by discharge. Discharge is cross-section area multiplied by velocity of molten metal. And molten metal velocity will be depending upon what? The height of the liquid or height of the sprue. And then sometimes if it is given the pouring basin also, we can select it there. Is it true? Yes. So I'll say that we'll trust Sandeep, and I'll say that's Delhi D is answer. So my name is actually, this is my name, Ravindra Thube. You can just go and check my Telegram channel. You can join that, and you can see that so many beautiful notes are there and everything is there. You can check these particular things. Yes, fine. Next question. What is the next question? Okay, one more question is there. Mold filling time in the second is. In a sand casting process, a sprue of 10 mm base diameter and 250 mm height leads to a runner which fills a cubical mold cavity of 100 mm size. the mold filling time in the second is. So how much time is required to filling the mold cavity? So the sand casting process, sprue of what? Bottom of the sprue has 10 millimeter base. That is the diameter. We have to calculate cross section area of the bottom of the sprue. It has a height of 250 mm. Leads to a cubical cavity. There is a cube cavity of size 100 mm. So everything is given there. So can I say that, sir, there is a cube, that is a cubical cavity of a size 100 mm. 100 mm, right, fine. 100 mm is the size of the cube, right, fine. So if the 100 mm is the size, can you able to calculate the volume of that? Yes, sir. Height of the sprue is given. What is the height of the sprue? Height of the sprue is given. 250 mm height is given. So I'll say that this is 250 mm. This is also given, 250 mm height is given. Then what is given? Sir, the base diameter is given. It's not a cross section area. Diameter of a bottom of the sprue. So cross section area of the choke or bottom of the sprue is what? Pi by 4 into d square, that is 10 square. Point to be understand here. Most of the students are making mistake. Most of the students are making mistake there at that particular point. Is it understood? Yes. So choke area आपके पास है. Rest of the value the there. So I'll say that, sir, time required is exactly equal to volume. What is the volume? It is a cube. Cube. Volume of cube is what? A cube or L cube. Length is what? 100. So I'll say that 100 cube is volume divided by choke area, that is pi by 4 into d square, right? That is a 10 square. Now we have to consider what? A root of 2 into g into ht. 2 into g, that is 10 into 10 to the power of 3. Multiply by height of the sprue is 250. 250 is the height of the sprue? Yes, 250 is the height of the sprue. So what will be answer is coming? I require answer from you now. If you don't calculate the answer, then why you are sitting over here? Quit and go and enjoy somewhere else. Why you waste valuable time? Time is very precise, right? Fine. Time is very precise. You should not violate your time. If there are 0 students, even if it is okay, but all the students should solve the question, then only there is a fruitfulness of this particular session. Volume divided by discharge. Discharge is what? Cross section area multiplied by velocity of molten metal into getting system. Chintan, very correct. 5.74. 5.74. My answer is 5.78 would be answer. 5.78 would be answer. Is there anyone who will be having the answer? Is there anyone who is having the answer? No one is there who having the answer. Nobody in the universe is having the answer. Is it that much difficult? Don't ask me that. I am selecting very simple question and these are the questions coming. That is what? Calculate the filling time, calculate the size of the pattern, calculate the volume of the pattern divided by volume of the casting, or volume of casting divided by volume of pattern. These are the simple questions that are coming in examination, my dear friend. Very correct, Sandeep. Sandeep and Chintan, I'm proud of you. Right? Very correct. So I'll say that, sir, answer is coming 5.7 seconds. 5.7 seconds. Right, fine. Now solidification time. Now you tell me that solidification time, how to calculate solidification time? There is one rule that is nothing but called as Chvorinov rules. So what is that? By Chvorinov rules, we know that the solidification time in the casting process, that is a solidification time in the casting, is exactly equal to K into what? Volume divided by surface area square. Do you understand that? Volume divided by surface area square? Yes. So from here, can I say that very easily? Sir, we can say that K is nothing but called as mold constant, or it is called as what? Solidification factor. It is called as mold constant or solidification factor. Right. What is mean by V? V stands for a volume of casting. V stands for a volume, right? Casting. And AS stands for surface area of a casting, from where here heat is dissipated to the atmosphere. Because we know that more and more the area is from where heat is dissipated to the atmosphere, can I say that the time required for solidification will be less. So therefore from here, can I say that solidification time is directly proportional to volume square? Is it directly proportional to volume? But it's not volume, it's volume square. It's volume square. Most of the time students are forgetting that square. Now, can I say that volume or solidification time is inversely proportional to surface area square, right? And we know that volume by surface area, that volume divided by surface area is nothing but called as a modulus of casting. It is called as what? A modulus of a casting. Do you remember that modulus of casting? Have you heard about that modulus of casting? Yes. And now on this particular, how beautifully questions were asked in examination. According to Chvorinov rule or equation, solidification time of the casting is proportional to. Now at least you tell me this answer. If you remember or if you understand that. There are 14, 15, 16 students are there. Out of that, can I get only 5 answers? Or all are observing that what I'm doing here? Right? Oh my God, students are just, okay, no answer. The solidification time of a casting is proportional to solidification time. Yes, yes, very correct. Solidification time of the casting is proportional to volume square. Just now you told me, sir. Sandeep Reddy, very correct. Yes, Sandeep Reddy, very correct. Is it true? Yes, that is solidification time is directly proportional to volume square. So I'll say that it is exactly equal to directly proportional to volume square. So it is proportional to volume square. Is it okay? Yes, A is the answer. Sandeep, Sirsha and Chintan, very correct. Next question. The relationship between total freezing time T, volume for casting V and the surface area Z according to Chernivers rule is. Now it seems very correct and very simple that right now, sir, what the silly questions you are asking right now, right here. But when it goes to the examination and then the real question is coming. You tell me that now what is answer? Solidification time T is exactly equal to what? Solidification time T is exactly equal to what? Sir, del D is correct answer. Volume divided by surface area square. Volume divided by surface area square. So I'll say that del D is perfect answer for me. No problem at all in this case. Volume divided by surface area square. Right, fine. Okay, now you solve this question and tell me that. Let's take a simplified question. There is a spherical drop. There is what? A spherical drop of a molten metal of radius 2 mm. So there is one spherical drop of a radius. So I'll say the radius of that particular is 2 mm, right? Spherical drop. And was found to solidify in 10 seconds. So that spherical drop is solidified in how much second? So time required for solidification T1 is exactly equal to 10 seconds, right? 10 seconds. A similar drop of radius 4 mm. Similar drop means what? Material is same. Casting conditions are same. So can I say that? We can say that, sir, there is a one particular drop of 4 mm radius, right? Can I say that? It solidifies in how much second? T2. How much second? T2. Can somebody calculate answer and tell me that? Del D is 40 seconds? Yes, calculate 40 seconds. Very correct. How to calculate that? So it's very simple. Solidification time required is exactly equal to, solidification time is required, exactly K into what? Volume divided by surface area. Volume divided by what? Surface area. Is it true? Yes. And it has to be square. Now what is the volume of the sphere? 4 by 3 pi r cube. 4 by 3 pi r cube is the volume. Is it true? Yes. Divided by what? Divided by surface area. Surface area is exactly equal to 4 pi r square and it has to be whole square. Now it can be considered this K will be common, 4 pi r cube and 4 pi r square, that will get cancelled. Can I say that it will come exactly equal to r by 3 whole square, and r by 3 is nothing but exactly equal to d by 6. R by 3 is coming simply r by 3 square. Is it true? Yes. Now we know that T1, how much is T1? I'll say that, sir, time required is 10 seconds for first. K is a constant, right, fine. R radius is what? 2. What is the radius? We know that, sir, 2 mm is the radius, divided by 3 whole square, divided by 3 whole square. Now this I'll be considering as equation number 1. This I'll be considering as what? Equation number 1, I'll consider this. And then the equation number 2. How the equation number 2 will come there? Same thing. So we required to calculate time required for solidification into K into what? Volume by surface area. Volume by surface area for the same sphere, again 4 by 3 r cube, and same thing r by 3. R by 3 here radius will be changed, that is 4 by 3. 4 by 3 whole square, right, fine. This will be equation number 2. You take a ratio of 1 by 2. Can I say that K will be same here? Why the K will be same here? Is there anyone K will be same here? Why the K will be same? Because, sir, it is the same procedure, same material, same conditions. So K will be cancelled. And only unknown is exactly equal to T2. So my T2 will come 40 seconds. How much answer is coming? T2 will come exactly equal to 40 seconds. Is it understood, everyone? Right, 40 seconds is the answer. Time required for solidification is exactly equal to if 40 seconds would be coming. 40 seconds would be coming. As simple as that. 40 seconds would be coming. Right, take a ratio of 1 by 2. Take a ratio of 1 by 2. Right, Chintan, very correct. D. Everybody understand this D is coming as an answer. Right, fine. Now, next question. A volume of cube of a side L. There is one cube whose side is exactly equal to L. And volume of sphere is exactly equal to volume of sphere of radius r are equal. That means there is a cube and there is one sphere. Cube and the sphere both are what? Equal. That's what exactly given. Both the cube and the sphere are solid and of manufacture of the same material. Both the cube and the sphere both are solid as well as manufactured from the same material. So material is same, right, fine. And most importantly, volume is same, manufactured from the same material. They are being cast and they are being what? Casted. The ratio of solidification time of the cube to the same of the sphere is ratio of solidification time of the casting to the cube. So, or sorry, ratio of solidification time of the cube to the same that of the sphere. So this ratio will be exactly equal to what? Because constant anyway is going to get cancelled. So what will be answer? A, B, C or D? Can you calculate? Sir, आप ही calculate करो, बोलो और चले जाओ. Right? So what is the answer? Can somebody calculate here? Can somebody calculate here? Sandeep Reddy, Sisra, Chintan, lots of students in there. Is there anyone can calculate here? Sir, it's very simple that if I select, there is a one particular cube. Let's say that this is exactly a cube. What is the length of the cube? Let's say that length of the cube is exactly equal to L. Length of cube is what? L. Is it understood? Length of the cube is exactly equal to L. Is it okay? Means what? Length of the cube is L. Right, fine. Then I'll say that, sir, what is exactly equal to surface area and volume? Volume is exactly equal to L cube. And surface area of this is exactly equal to what? The cube has 6 faces. So I'll say that 6L square. 6L square. That will be exactly equal to volume by surface area. Now I'm selecting one particular sphere. Sphere of a radius exactly equal to R. Sphere of radius exactly equal to R. If the sphere of radius exactly equal to R, what is volume? Volume is exactly equal to 4 by 3 pi R cube. 4 by 3 pi R cube. And surface area is exactly equal to what? That is a 4 pi R square. But volume by surface area, can I say that the volume by surface area is coming exactly equal to R by 3. R by 3. Is it understood? R by 3 aayega. No issues. And here also volume by surface area, what it will come? Volume by surface area, can I say that it will come L by 6. It will come L by 6 volume by surface area. L by 6 is coming. And now we are interested to calculate ratio of what? The solidification time of the cube to that of sphere. So I'll say that here the solidification time for a cube, that is exactly equal to constant K into volume by surface area. V, I'll keep it as it is. Or I'll say that volume of this particular cube divided by surface area. What is the surface area? So I'll say that 4 pi R square and whole square. I'll call this is that equation number 1. And this is what exactly is sphere, right? Fine, sphere. It is exactly equal to K into volume of a sphere S divided by surface area of the sphere. Oh my god, this is not a sphere surface area, so I'll say that 6L square will be correct and this is 4 pi R square will be correct. Now sir, whatever volume by surface area you calculate, that is not even required to calculate. You take a ratio of these two equations. If I take a ratio, can I say that solidification time of the cube divided by solidification time of the sphere, solidification time of the sphere is exactly equal to K will get cancelled. This 4 pi R square will come to the numerator, 4 pi R square divided by 6L square, and this entire whole square will be there. If you do that, 4 pi and the 6 you come common, it will be square. Then it will come R by L. R by L, that is what? 4 to the power of 4, because 4 to the power of square, that is what? 4 will be coming. Is it true? Yes. So what will be my answer? My answer will be exactly equal to del D. My answer will be exactly equal to what? D. So I'll say that, sir, my del D would be perfect answer for this. Del D would be perfect answer for this. 4 pi by 6 square R by L to the power of 4. R by L to the power of what? 4. Right, fine. Now there is one more question is there. Yeah, I'm asking the students that, what do you expect from this session? All the students who are there attending, whatever it may be, can you write down that what do you expect from this session? Do you expect me to cover a theory or fundamental? Or do you expect me to cover questions and numericals? Or what is your expectation actually? What do you expect actually in these sessions? Can somebody tell me that what do you expect? Or you expect nothing? What do we expect from this session? That is what my answer is, question is. Numericals? Chintan, numericals, more and more numericals you require? And we should keep on solving numericals only? Okay. Okay. Okay, let's solve next question. What is the next question is coming? So the question is that while cooling, a cubical casting of 40 mm undergoes a 3%, 4% and 5% volume shrinkage during the liquid state. So can you understand that there is a 3 stages is given, that is the volume shrinkage takes place in liquid stage 3%, Then there is the solidification or phase transformation shrinkage takes place 4% and 5% takes place in a solid state. That is solid state. The volume of metal compensated from the riser is. So how much percentage of volume? Both theory and numericals. Okay, fine, Sirsa. Okay, great. So what will be your answer? So how much percentage of volume of material will compensated from the riser? Riser kitna compensate karna chahiye? An answer is given 2%, 7%, 8% and 9%. How much volume should be compensated by the riser? That's what exactly question is. That's what exactly question is. How to connect you? You can write down my or search my name on the Telegram. The name on the Telegram is Ravindra Thube, and there is one channel Ravindra Thube by name. So you can just particularly join my Telegram channel and we can connect, right? As simple as that. Okay. Yes. So you tell me that what is the answer? So it is given that the liquid shrinkage is 3%, solidification shrinkage, that is the transformation phase, is a 4%, and then a solid contraction is a 5%. Therefore, that means if I consider this is A, if I consider this is B, if I consider this is C, and if I consider this is D, so can I say that liquid shrinkage has taken place? Liquid shrinkage taken place, that is from A to B, whatever shrinkage takes place, it is exactly equal to 3%. And whatever shrinkage takes place from B to C, that is exactly equal to 4%, right? Fine. And then C to D, that is a solid contraction, that is again 5% is coming. But sir, liquid shrinkage is only compensated by providing riser in the system. So can I say this is my liquid shrinkage plus solidification? It is only a liquid shrinkage. So this is my total liquid shrinkage. This is my total liquid shrinkage, and that liquid shrinkage is compensated by providing what? Riser. Riser is provided. Riser is utilized to compensate liquid shrinkages. So in total how much? 4 plus 3, that is 7%. Absolutely correct, Chintan. 7% Sirsa, very correct. So I'll say that sir, 7% would be there. 7% would be there. Right, fine. Is it true, everybody? Yes, so 7% is there by which we can be able to compensate that. As simple as that. Right, fine. Now this is very interesting question now. What is that question? Take. A cubical casting of 50 mm side undergoes a volumetric solidification shrinkage and volumetric solid contraction of 4% and 6% respectively. And point to be understand here, most of the students are commit mistake. What is that? Volumetric solid contraction and volumetric solid shrinkage is respectively given 4% and what? 6%. No riser is used in the system. Assume uniform cooling in all direction. Uniform cooling takes place. The side of the cube after solidification and contraction is after solidification and the contraction. How much will be the side? How much will be a side? That is what exactly answer is. Cubical casting of 50 mm side undergoes blah blah blah. Answer A, B, C or D. To run your show and tell me that how much exactly could you answer. You calculate answer and tell me that what exactly the answer is. What exactly the answer is. Is it understood, everybody? Is it understood, everybody? Yes. Tell me what is exactly answer is. Tell me what is exactly is answer is. Can you calculate answer? Everybody has to put your pen and the pencil and the paper, whatever it may be, and then start and tell me that how much exactly equal to answer is coming. How much exactly answer is coming. Is there anyone who can calculate answer? So it's very simple. A cubical casting is of 50 mm side. Alright, fine. I'll tell you that. Cubical casting. Where is the cube? Sir, this is my cube. And what is the size of the cube? Sir, size of the cube is exactly equal to 50 mm. What is the size of the cube? Size of the cube is exactly equal to 50 mm. 50 mm is size of the cube. Right, very true. Okay, is there anyone who got the answer? So length is exactly equal to 50 mm. Is there anyone who calculated any answer? Agar hai to tell me that. Right, fine. Agar hai to tell me that what answer is coming. And now it says that volumetric contraction. That means volume is shrinking by 4%. Volume is shrinking by 6%. And in successive stages. It's not a 10% total. So if I calculate original volume, how much is original volume? Original volume is exactly equal to 50 cube. Because it is what? A cube. Volume of cube is what? Volume of cube is 50 cube. Now this volume first of all shrink by how much percent? 4% volume shrinkage takes place. If the shrinkage in the volume is 4%, then how much will be remaining? Remaining will be 96% of the total volume. So can I say V1 volume will be 0.96 multiplied by 50 cube. Is it true, everybody? 50 cube. That is shrinkage in the volume is 4%. The remaining kitna? 96%. And now this volume furthermore gets shrink. Furthermore, it will get shrink by how much? It will get shrink by a 6%. In a successive stages, it is shrinking. So now what will be volume V2? V2 will be exactly 94 of that particular V1. So 94, that means 0.94. into 0.96 into 50 cube into what? 50 cube. So how much is the volume V2 is coming? And that will be a volume, and the volume will come, can I say that will be volume, but because of the contraction, can I say that the size of this particular casting will also change? And let's say that now the size of the casting of after the contraction in the volumetric takes place is exactly to L1. Uska volume we know how. Can I say this volume will be exactly equal to L1 cube? So can I able to calculate L1 value there? That whatever the volume we calculated V2, that is calculated after a couple of shrinkages take place in the volume, 4% and 6%. That is the volume. And we know that cube volume is exactly to L cube. So side L1 can be calculated from here. So L1 will be coming exactly to anyone. Anyone in this session can able to calculate that? No, sir. We can't able to calculate. You tell me answer, and then that would be better. That is 48.32. 48 point what? 32. 48.32 would be answer. 48.32 would be my answer. Is it understood, everybody? Is there anyone who understand that? Okay, fine. This is what exactly my answer is. 48.32 millimeter. Right, fine. So A is exactly my answer is. A is my answer. A is my answer. A is my answer. A is my answer. Right, fine. Now riser, we know that riser is basically utilized to compensate what? Compensate liquid shrinkages taken place. Right, fine. Next question. So this is what exactly a question it was given, that a sand casting, a sand casting mold assembly is shown in the given figure. The elements marked by A and B are respectively. What is A and what is B? At least tell me this answer. What is A and what is B? What is A and what is B? This is theoretical question now. Right, fine. Gate is not mentioned in the figure and diagram. Okay, let it be. It was mentioned like this. So what is A and what is B? That is what answer is. Can somebody tell me what is A and what is B also here? Or that also we cannot understand what is A and what is B? So we can't understand what is A and what is B even. That means there are no students sitting over here. That's the story, right? No Chintan, no Shirsha, nobody, right? Can anyone tell me that answer? What is answer? So what is A and what is B in this particular figure? No one. I'll say that A is exactly equal to my riser and B is exactly equal to my sprue. A is exactly equal to riser and B is exactly equal to sprue. A is riser, B is sprue. A is riser and B is exactly equal to sprue. So I'll say that, sir, this is my A, riser, and this is exactly equal to sprue. So del D is my answer. Del D is my answer. Del D is my answer. Is it understood, everyone? Is it understood, everyone? Oh my God. This is the story and the life we are living in. Okay, anyway. Okay, no worries. Okay, this is the question that is, you can go and calculate answer by yourself. Right, fine. I hope so. You tell me that. Now, tomorrow also I have a session. And in tomorrow's session, I am trying to cover a metal casting. Metal cutting. Tomorrow there is a one session. I am trying to cover metal cutting in tomorrow's session. Now you tell me that what exactly you are expecting from me in a metal cutting, so that you will come and join and you'll enjoy the session. Otherwise, we'll cancel the session, because these sessions are only for you. You have to brush up your knowledge, then you have to come, you have to solve the numericals, and you have to give me answer. Right, fine. And if you are not being interested in doing that, then there is no point in conducting such sessions. Right, fine. We are doing that. Right, fine. This is question you can be able to solve. There is no big deal. So can anyone tell me that what is expectations? How many questions I should solve and what exactly expected? Should I go boom, 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 only a questions, tuck, 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 numericals? Or even you are not solving the numericals also? You write down your expectation in the comment box, or otherwise if you don't want to comment and communicate with me, and that is also even okay. Is there anyone who knows me previously? I mean, somewhere in the other platform, in the previous platform, or somewhere we had interaction. Is there anyone who knows me also in that session? Or no one knows me as prior to this particular session? I don't think so. Is there anyone who is connecting with me? Right? So, Hania Amer, VIT college. That is in the Pune? Oh my God. Right. VIT. I was there in the VIT. Right. Way back in 2012 or 13. Okay. Hani Amir, you can connect me my Telegram channel and then you can connect with me. No problem at all. Right, fine. So this question you could be able to solve, and if there is any suggestions you can write down on my Telegram channel. So this is what exactly we want. We'll try to come up with that. Otherwise tomorrow I'll come with only numericals. Very handful of numericals will come and then we'll try to solve. I understand that I should have my answers because you are not going to solve the answers. Right, fine. So let's see that. So take care of yourself, right? God bless. We'll see you in the next session, right? Thank you all. Bye-bye.